I know you guys were waiting for me. Heard a lot about you. Oh no, we already video chat once. Yes. Yeah, well, you forced us. Yeah. No. Yes. You called and then you were like, hey, come. No, I don't know. I never met you. No, we never met in person. I wasn't there, I remember. I'm sorry. Guilty. How could you? What? By the way, okay, I'm sorry. I thought it was like somewhere in Czech, like I don't know why I thought that. I'll tell you mine. 2020, all of 2026. Just to be sure. Contract ends July 2026. Yeah. Ja, ja, we zijn moeilijk de bek in. Yeah, I want to use it. Do I? But it was not bad. That's what I wanted. Very happy. But I think
Please be seated. Welcome everyone to this public doctorate committee of the PhD candidate Manish Pandey on the topic of centrality measures and connectivity properties in large networks. My name is Joost Kok and I'm the Vice Dean of the Department of Mathematics and Computer Science. I will be chairing this session. Every defense is a special occasion since it marks the end of an intensive period of research. We are looking forward to the defense and I think we'll have an interesting hour. I hereby formally open the defense. I would like to invite the candidate to come forward. The candidate can take the position behind the lectern. We welcome all committee members to join this session, in particular those members from outside the Eindhoven University of Technology. Our university very much values the presence of experts from outside our own university on PhD defense committees. The time investment is considerable, both for reviewing the thesis but also for the defense today. I would personally like to welcome Professor Atreya. He's present online. Professor Atreya is from the International Center for Theoretical Sciences, the Tata Institute of Fundamental Research in Bangalore, India. Welcome. And also would like to welcome Professor Waldman of Leiden University. Welcome to Eindhoven University of Technology. Also present in the committee is Professor Litvak from Eindhoven University of Technology. And also present are the promoter and the co-promoter, the promoter Professor van der Hofstad and the co-promoter Professor Exarchakos. I would like to ask the promoter to start the events.
Geachte promovendus, can you please summarize your thesis in at most 10 minutes?
Yes. Good evening, everyone present either physically or online. I'm here to defend my thesis titled Centrality Measures and Connectivity Properties in Large Networks. So firstly, I would like to address that I would like to simplify the term of my thesis. It consists of three technical terms: centrality, connectivity, and networks. Let's just dive into what are networks. So networks are mathematical structures which indicate pairwise relationships between objects. These objects can be vertices, are called vertices and nodes. These can be people, cities, chemical compounds, biological networks, and anything which you can think of. So networks are present all around us, but the most common example that we see every day around us is the social network. So as you can see in this picture, that people are connected through social media sites like Twitter, Instagram, LinkedIn, whatever, and a lot of other social media sites that we have. But there are other examples as well, like the transportation network, where the nodes are basically cities connected by roads. So these relationships can differ, but you understand what it is. So then let's come to what is a centrality measure. So network scientists introduce the notion of centrality to define a node, if a node is important or important, less important, or more important. So how they define it is like they assign numerical values to the nodes to indicate how important they are. If the value, if the value is large, it means they are more important, and if the value is less, that means it's less important. So certain very good easy examples are degree centrality, which is in a social network. You can it's just basically a popularity index, how popular you are in a network, like how many friends you have or how many followers you have. But this is not the only metric to see how important you are. You can look at other measures like closeness centrality, which in a transportation network, you are not interested in how popular a city is. Like you are more interested to know how close it is to other cities. And there are many other. There is a plethora and a jungle out there. Lots and lots of centrality measures are there, like betweenness. And you can see in this figure that they indicate different types of measures of importance. So there are, in my thesis, I address other centrality measures which are difficult to explain, but I'll just mention them briefly, like page rank, CADS, eigenvector centrality, and many others. But I would like to put a special emphasis on page rank because of its huge applications. So, before the dawn of 21st century, Larry Page and Sergey Brin, they wrote a paper about the founders of the Google. They introduced something called the page rank centrality measure, which kind of revolutionized the 21st century. And suddenly, so the World Wide Web, which consists of billions of nodes, it's very complicated network. So searching something, whenever you search something, you get the results you desire in the first search itself. That's a miracle. That's a miracle of mathematics, and a miracle which is done by this algorithm called PageRank. First of all, I would like to emphasize that these centrality measures are really different. So you can look at this picture. So this is a color projection of the centrality measures. Dark means you are more central, and light means you are less central. And you can clearly see that both the centrality measures are really different for this network. So, which brings me to the two main questions that we address during the 4 years of my thesis, which is how can so the question number one: given two centrality measures, can you tell which one is better? And the question number two: given two centrality measures, can you tell if they are similar or very far apart? So let's just dive into method 1, which is the vertex removal procedure. So what we do is, as the name suggests, we remove vertices. So how we remove vertices? We look at the most central vertices, and so what happens is that the graph fragments. It breaks down into sub-networks, smaller networks. So the centrality measure, which is able to fragment the network at a faster rate, could be considered in some sense to be a much better centrality measure. That's a qualitative way of comparing two centrality measures. I'll show you by an example. So look at this. I'll be using the same network for the comparisons. Wait a minute. Sorry. Sorry. Okay. Instead of putting it. Okay. Yeah. So I'm using the same network for the for illustrating the methods. So in the left, you can see with respect to closeness centrality, when you remove the top 20% nodes, you get left picture, and with degree, the same thing you do, you get the right picture. So you can see that in the left, closeness centrality is able to break the network in a much faster rate, which means closeness is better than degree for this particular network. But it is possible for other network, degree might be better. But for this network, you can compare. Similarly, you can also compare other centrality measures like betweenness, page rank. In this example, here betweenness performs better than page rank. So the crux of this method is that you remove vertices with respect to the centrality measure, highest ranked vertices, and you look at the connectivity properties. So for our case, we use the two properties called the size of the largest connected component, which are also called the giants, and the second property we use is the number of connected components. But you can use any other connectivity properties, whichever you feel like. It can be something else as well. Yeah. So let's dive into the second method, which is a quantitative method of comparison, which we call the centrality comparison curve, or the CCC, to make it sound a little bit easier. So CCC. So first I will tell about it naively. So if you get a curve from two centrality measures. If the curve is a straight line, you can say that they are similar. If the curve is a quadratic line, like the orange curve, you can say that they are very different. The ranking induced by them are basically independent. So I'll show you. How it performs is, you look at the top X% centrality measures from the first centrality, and look at the top X% from the second centrality, and look at the overlaps. So if everything is overlapping, they are essentially the same centrality measures. But so you can characterize with the curve, you can characterize the behavior of two centrality measures with respect to each other. So this example is betweenness and load. The blue line indicates the actual curve. So the curve is in the blue, so that means they are very similar for this network. And the second example, it shows the quadratic curve. This is for between page rank and out degree. And this means that they are essentially the ranking induced are independent. Similarly, you can have a relationship which is in the middle of the both, like neither exactly dependent or very independent, they are in the middle. So apart from discussing two methods, in my thesis, I also work on a bit more there, which are also network applications, which I would like to discuss briefly. So one, in the chapter 6, I talk about cascade dynamics in networks, so cascading is basically a phenomena in networks. Like what happens is a small initial event, it triggers a chain reaction, and in the network, and the network kind of gets destroyed, and a very strongly connected component is left later on. So we look at the properties of this core in chapter 6, and as a second example, the second application of networks, we look at the satellite interferometry. So what the problem is that in deep space you have low frequency radio waves which tend to get dissolved as they enter the atmosphere because of lot of disturbances. So what happens is that to read those data, the satellites have to communicate. So you have to send the satellites in the space, and they communicate with each other in order to cross correlate the data between themselves and send it back to Earth. So you need to optimize and look at a lot of mathematical properties. So we do that in chapter 6, and that's what I wanted to discuss in my slides. And I would like to thank you for your attention. Yeah, that's the end of my
Thank you. Thank
presentation.
you also for keeping the time. May I now ask Professor Atreya to ask his questions?
Can you hear me?
I can't hear you.
We cannot
Am I
hear
audible
you.
now?
Do you have your microphone on?
Yes, microphone's on. Yeah. Unmuted.
We can't hear you. I'm sorry.
1 second.
No, we cannot
I'm
hear you.
unmuted
We have
right
to
now.
ask
Can
for
you
some
hear me?
assistance. So maybe we can. I will ask for some assistance, but in the meantime, maybe the secretary can maybe ask for some assistance. Then we might continue with Professor Waldman at first, and then later come back to you, Professor Atreya.
Okay.
Thank you, Mr. Chairman. Dear candidate, I first of all would like to let you know that I really enjoyed reading your dissertation. I have a few questions that I would like to ask
They have
you.
a problem local.
My first question is about the nature of the networks that you study in your dissertation. And to introduce that question, I need to perhaps very briefly say something about my own work around networks. So I study a lot of networks in the field of quantitative science studies, networks like citation networks, networks of, for instance, collaboration, co-authorship between researchers, also networks derived from textual data like scientific articles, co-occurrences of terms in articles. And when I read your dissertation, I noticed an important difference between the networks that you are studying and the networks that I typically study. So the networks studied in your dissertation are unweighted. The networks that I mostly study are weighted. So the edges between the vertices have weights, like for instance, the number of times two researchers have co-authored, or the number of times two scientific terms occur together in scientific articles. My question for you is, to what extent you believe the results in your dissertation are also applicable in weighted networks instead of unweighted networks?
Okay. Hugul, dear opponent, thank you for your kind words and that very nicely phrased question. So your first question was about the nature of your question was about the nature of the networks that I study. So yeah, so most of the networks which I have like mentioned in the thesis are not weighted, but I think the similar analysis can be performed for networks which are weighted as well. But I have in my chapter 6, I have also mentioned citation networks, which you mentioned briefly. So we do an comparison, that centrality comparison curve. We perform that on the citation network. But you can define centrality measures for weighted graphs as well, like the shortest distance metric, the betweenness centrality, the closeness centrality. All of this like depends on the edge weights. Might change a little bit, and you can do the similar analysis like the vertex removal procedure, because you can again get centrality measures which are based on the weights of the edges. You can define those centrality measures in a little bit different manner, and you can now talk about vertex removal procedure for the weighted networks. And similarly for the CCC curve, again, because you now have a centrality measure based on weighted graphs, so you can rank them accordingly and talk about the centrality comparison curve for these two types, these weighted graphs as well, and do a similar analysis on. And I don't think that this might change like the proofs, the convergence results that I have. I hope, but I think very strongly that they won't change. But obviously, you have to check it in the paper and with a paper and pen. But yeah.
Yeah, perhaps I could actually follow up on one of the things you mentioned. So you mentioned the vertex removal procedure.
Right.
And I think I agree that that procedure can still be applied in weighted networks.
Yes.
However, in practice, when I look at the networks that I am studying, they are not only weighted, they are also very dense. So typically these are networks in which almost all the vertices are connected.
Right.
That's, for instance, what you get when you make networks of term co-occurrences based on textual data. All the terms usually occur at least once when you have a big corpus of text. So the network is really dense. And I was wondering if the whole idea of kind of using connectivity as the basis for the vertex removal procedure, looking at a number of connected components, if that actually still works in these types of networks, the networks that I just mentioned, the networks that are not only weighted but also dense.
For dense networks, the comparison might not work as better, because like removing some little bit vertices might not affect the connectivity that much. But for dense networks, this is the second method, the centrality comparison curve. You can like it's very nice a comparison technique that works even for both cases, like the sparse and the dense regimes. And recently we were also thinking about the dense how to like the recently we are thinking about how to like solve the convergence results, define the centrality comparison curve for the dense regime in a very rigorous way, like using graphons and stuff. But that is still under work. But this method is not a qualitative comparison, it is a like a quantitative comparison. It just tells you like how similar two centrality measures are. So in case you have very highly computationally very heavy method centrality, or you have like less computational heavy centrality, you can, if you can like say that they are similar, you can use the easier one. So that's my answer.
Okay, thank you. I actually do have a question that relates to what you just mentioned, the centrality comparison curve, the CCCs.
Yeah.
I must say I find the CCCs extremely interesting. When I read about it, I thought, oh, that's really, really, really interesting. I was puzzled by one particular thing that is in the discussion of these curves in chapter 4. So you make the point that these curves are invariant under monotone transformations,
right,
which I agree with.
Yeah.
But you then also state, it's on page 92 of your thesis, you also state that correlation measures, correlation coefficients measure a linear dependence. So that is on page 92. In the discussion of the invariance property, you state that your CCC approach is different from traditional correlation-based approaches, because these correlation-based approaches focus on linear dependence.
Yeah.
And for me, that raises some questions, because I do agree that things like Pearson correlations are indeed focused on linear dependence. But at the same time, we also have lots of other correlation measures that are of an ordinal nature, and that therefore have this same property that you are emphasizing so much, this property of being invariant under monotone transformations. So my question basically is, although the CCCs are interesting and fascinating in many ways, do we really need them? Because we already have these more kind of traditional tools of ordinal correlation coefficients, Spearman correlation, for instance. So do we really need the CCCs?
So the CCC is based on rank, and ranks cannot go